Hi and welcome back. Today we're going to be looking at how we can deal with weak acids and weak bases in terms of pH calculation, and this will be involving the use of pKa and pKb. So let's get started. We know that in aqueous solution weak acids and weak bases don't dissociate completely. Essentially, we know that ionization is only partial, that it sits in an equilibrium system, and for each of those equilibrium systems we could write an equilibrium expression. So if we were to write the ionization of a weak acid, we have the acidic proton and the A standing for the rest of the acid, plus water, because this is going to be ionization in water. We have the equilibrium arrow, and we will get H3O plus A minus, being the anion that forms from the ionization. This equilibrium system can therefore have a equilibrium expression written for it, Kc, where we have the products H3O plus and A minus over the reactants, which are HA and H2O. Mathematically, the value of H2O is going to be approaching 1, this being because the concentration of H2O compared to that of the acid in any aqueous system is going to be so much more. So what happens is we remove the concentration of H2O from this equation, and our denominator just becomes the concentration of the acid. Remembering all of these are equilibrium concentrations. The same can be said for a base, where we have the initial general equation being the base, remembering bases are proton acceptors, plus H2O, in equilibrium with the formation of the positive ion of the base H+, so essentially picking up the hydrogen. It may be negative because the base is likely to be negative, so this may be neutral, plus OH minus. This is just the general form of a base accepting a proton in a Bronsted-Lowry reaction. Again, this means that our Kc will be equal to the products, which are going to be BH plus times OH minus over our concentration of the base. Okay, remembering that these will change with the coefficients, that we would have to raise them to the powers if the coefficients were, say, 2. In this case, we would then get Kb being BH plus OH minus over B. So this gives us now the expressions at equilibrium for a weak acid or a weak base ionization system. Essentially what this is saying is that if we look at a strong acid, we assume complete ionization. A weak acid is partial. So the Ka will give us an indication of how acidic the substance is, the extent of reaction to the right, i.e. how much ionization has occurred. This means that if we have a very small Ka, the extent of ionization to the right won't be much, so we will have a very weak acid. If it was a large Ka, then we would have a stronger acid. For Kb, this gives an indication of how basic the substance is, i.e. the strength of the base. And as with Ka, if we have a small Kb, then we have very little ionization. For a strong base, we would expect a very large Kb value. We essentially assume it ionizes all the way. But with a partially dissociated weak base, we will have a small Kb value because we would have a small value for the products on top being divided by a larger value of the non-protonated base on the bottom. As we've mentioned before, when we say pH, taking the p of something means to take the negative log to base 10 of that. So the pKa is given the equation the negative log to base 10 of the Ka value, and the pKb is the negative log to base 10 of the Kb value. The larger the pKa, the weaker the acid because of the inverse, and the larger the pKb, the weaker the base. These tables of pKa's and pKb's are given in your data booklet, And as you can see, methanoic acid has a pKa of 3.75, 4.76 for ethanoic acid. Nitrous acid is 3.14. Hypochlorous and boric are at 7 and 9. So remembering that as the pKa increases, the strength of the acid decreases. Same goes with the base. You receive tables of the base information. The smaller the pKb, the stronger the base. So one of the first skills that we need to be able to do is essentially refresh our knowledge on equilibrium and write equations for the ionization and then the expressions for Ka or Kb, just remembering that these are equilibrium expressions. So for the first one, it's going to be a Ka. We have the CH3COOH, liquid plus water, liquid, in equilibrium with the ionized forms. So CH3COO minus aqueous plus H3O plus aqueous. Okay, so that would be the ionization. This is an acid, so we're going to have a Ka value, and that's going to be the products, CH3COO minus, over the reactants, removing water, so now it will just be CH3COOH. So now we have the full expression for the Ka. For the Kb, again, we're going to have ammonia reacting with water. Ammonia is going to act as a base and form NH4+. Plus OH minus. So our Kb is going to be NH4+, the conjugate acid, over the times the OH minus, all over the base, removing water. So that should be a fairly nice mark if you're given that type of question on the exam, which you will see. The other kinds of things that you can see is these two questions here. So if we look at worked example 1, going on from what we've seen before, ethanoic acid is the principal acid in vinegar. Write an expression for the acidity constant. That's what we've just done there. We first write the equation and then write the expression for the constant. Always remember to write the equation. And then in worked example number 2, we're asked to compare the acidity of boric acid, methanoic acid, and propanoic acid. So you will go to the table in your data booklet, this reference is wrong, and find the pKa value for these substances. Boric acid has 9.24, methanoic 3.75, propanoic 4.87. So the larger the pKa value, the weaker the acid. So these three substances, put in order, boric will be the weakest, methanoic will be the strongest, and propanoic is going to be in between the two. So when we give our order, we just put it from the largest value to the smallest value because it's asked us to give them in comparing the acidity. So the weaker the acid, the less acidic that it is. Okay, so here is another style of question that we have for these. And this one says, if benzoic acid has a pKa of 4.20, calculate its Ka. Remembering that the pKa is equal to the negative log to base 10 of the Ka. This parallels our idea that pH is equal to negative log to base 10 of the H3O plus, and that we can then write H3O plus is equal to 1 times 10 to the negative pH. Then we could rearrange this in the same way, and we can get that the Ka is going to equal 1 times 10 to the pKa. Once we do that, we will end up with this form here. Plug in our value of 4.2, plug it into our calculator, and remember to give it a unit. Okay, so this will be 6.3 times 10 to the negative 5 moles per decimeter cubed. Okay, that's it for these types of calculations. Next up, we will look at ways where we can substitute values in, like we did for our equilibrium constants, and determine the value of Ka in an equilibrium system from concentrations rather than from the pKa values. I'll see you in class.